The topic that we'll be talking about today is thermometers and the types of thermometers. There are different types of thermometers and there are different properties that they work on. Before getting into the types of thermometers, we will be first talking about the basic difference between heat and temperature because uh, they're not really interchangeable, but when we talk about heat and temperature, we do tend to mix them up. The next thing that we'll be discussing is the need for different types of thermometers and why we have different type of thermometers, and then we'll get into the classification of different thermometers. First one being liquid in glass thermometer. Second one, how this is not a type of thermometer, but we will be talking about how the scale of temperature is basically set in a thermometer and how we know that certain scale or range is sufficient for our use or the application that we are going for. Second type of thermometer that we'll be discussing would be clinical thermometer, then thermocouple thermometer, and then other thermometers. We won't be discussing them in detail since they are not as majorly discussed in the syllabus. So it is important not to confuse the temperature of a body with the heat energy that can be obtained from it. Heat passes from a body at high temperature to one at a lower temperature. This is because the average kinetic energy of the molecules in the hot body falls as a result of the collisions with molecules of the cold body, whose average kinetic energy is lesser, and therefore the temperature increases. So that's how basically the energy propagates, and energy doesn't propagate, but energy is transferred, or how the temperature is basically increased. So when the average kinetic energy of the molecules is same in both bodies, they are at the same temperature. We say that they are at the same temperature. Heat is also called thermal or internal energy. It is the energy a body has because of the kinetic energy and the potential energy of its molecules. So um, increasing the temperature of a body increases its heat energy because the kinetic energy of the molecules is increased. So what basically happens is that we do tend to mix them up because yes, if we increase the kinetic energy, the temperature of a body, the kinetic energy obviously increases. But um, the main concept here is that what is heat? Heat is basically a measure of thermal energy or internal energy. It's better to say internal energy because we do associate therm with temperature. But let's just say we call it internal energy, then we're taking in account of all the kinetic as well as potential energy. So I'm going to write internal here. So that's internal energy. Now, what does internal energy actually contain? This is internal. It does contain this huge significant portion of two main things that one of them we've discussed very vastly. Um, that is kinetic energy and potential energy. Now, by potential energy, I don't necessarily mean elastic potential or gravitational potential energy. Potential energy can be any kind of stored energy that an object, GE, I had to write DE, yeah. Why did I write GE? I'm gonna turn it into PE, potential energy. I guess I was talking about gravitation. Okay, so potential energy doesn't necessarily mean that we're talking about gravitational potential energy or elastic potential energy. It refers to any kind of energy that an object can possess because of its position or the state that it is in. It is stored form of energy. So that energy can be because of magnetism, that energy can be because of the inner forces of the object, of the molecules. So all those forces combined are potential energy, then that combined with kinetic energy, we get internal energy. So if we take this small element out and we talk about kinetic energy only, then it's kind of okay to interchange these terms because temperature is really directly proportional to the kinetic energy. Absolute temperature is really directly proportional to the kinetic energy of the molecules of a body. So that's basically about the difference between the internal energy and uh, sorry, the heat and temperature, which we've made it really clear. So um, the reason why the increasing the temperature of a body increases its heat energy is because the kinetic energy increases, and kinetic energy is really a huge part of internal energy. So that's why. Um, Okay, so now we'll be talking about types of thermometers. There are different types of, jobs. There are different kinds of thermometer, each type being more suitable than another for a certain job. Each type, the physical property used must vary continuously over a wide range of temperature. It must be accurately measurable with simple apparatus and vary in a very similar way to the physical properties. So basically, the thing is that when we're talking about the the temperature and measurement of it, it's really important to just keep it uh, to have a property that varies linearly with the temperature. Let's just say if we're talking about linear expansivity, or if we're talking about the the change in resistance of a thermistor, let's say, the major part to really note in this case is that whatever property we're considering, that should always be it should always be linear to the change in temperature that we are going for. So coming to the first type of basically thermometer that we'll be talking about, liquid and glass thermometers. Now these are the main common ones, the common thermometers that we see in our daily lives, or the ones that we have at homes that we use to really get an idea of the temperature of the body when someone is feverish or sick. So in this thermometer, what happens is that uh, in this type, the liquid is in a glass bulb and it expands up the capillary tube when the bulb is heated. Now, the capillary tube is basically like a storage, or it has some liquid in it or some medium in it that expands and that moves up the capillary tube as there is some change in temperature. Now, the reason why it's a capillary tube is because capillary tubes are really, really thin in their length, sorry, in their width. So the expansion is really linear. The expansion is towards the length side or the length section. The liquid must also be easily seen, so it's important that it is either colored. Let's just say we're talking about liquid, let's just say any transparent liquid, it's uh, in order to see the meniscus or the level of the liquid that had expanded, it's important to make sure that it's colored. So usually, however, the ones that we have at homes or even at some clinics, if they're not using clinical thermometers, and they have mercury. So mercury in glass thermometers are really common example that we can see. Another thing is that it must not stick to the inside of the tube, or the reading will be too high when the temperature is falling. So the viscosity, the surface tension, all of these factors are really important when considering the inner liquid of the bulb. So the basic optimum option that we're left with is always most of the time mercury, especially when we're dealing with body temperatures. So mercury and other colored alcohols are usually used. Mercury freezes at minus 39 degrees and boils at 357. So that gives us a really moderate range for our usage. And similarly, alcohol freezes at minus 115 degrees and boils at 78 degrees. So that's also something that we can work with. Okay, now how is like a scale of temperature really defined? We've talked about the freezing and the boiling temperatures of different mediums that can be used inside the bulb of thermometers. That's a really important point that is considered when building up a thermometer or deciding the scale of temperature that thermometer will measure. A scale and unit of temperature are obtained by choosing two temperatures. They're called fixed points, and then they are divided among the range between them in equal number of divisions or degrees, as we call it. So, on the Celsius scale, that is named after the scientist who suggested it, the lower fixed point is basically taken as the melting point of ice, which is 0 degrees, since zero is like, a common scale point. So, it's really smart to use that calibration or use that as fixed points. The upper fixed point is the temperature of steam that is approximately 100 degrees. So 100 to 0 is really like a proper scale with 100 numbers of divisions. So that's the main, the common or the prime scale that we usually go for, taking the lower fixed point as the pure melting ice temperature and taking the upper fixed point as the water boiling steam temperature. So when the fixed points have been marked on the thermometer, the distance between them is divided into 100 equal degrees. The thermometer now has a linear scale. In other words, it has been calibrated or graduated. So what happens is that we have an ice point and then we have a steam point, as it is written right over here. This is the ice point, which is at 0 degrees as we set the lower fixed point, and then we have a steam point, right? So it is 100 degrees. Now, we have these 2 points. I know that when it is 0 degrees, the bulb, sorry, the liquid in the bulb, it rises to this level. So I'm gonna mark it as 0 over here. Like, right, if I have this just liquid, sorry, this glass container that is thermometer, I just make a mark over here and mark it as 0. Since I have taken a medium that is mercury that does expand linearly, I do not have to worry about other calibration. So the next thing that I need is an upper fixed point. It can be 500 degrees, it can be 20 degrees, 30 degrees, whatever. But we choose to take steam point that is 100 degrees as the upper fixed point. So the next thing what I do is I'm going to immerse this thermometer in boiling hot water because I know that temperature is definitely going to be equilibrium 100 degrees. So what I need is the point where this level of mercury rises to when it is immersed in 100 degrees. So I'm going to do that. As I put this thermometer in a flask where with boiling steam, the mercury level is going to rise to some level, which in this case is right over here. So it's going to rise to this level and I'm going to mark it as 100. Now the next thing that I do, since again I'm mentioning it again and again, that since I know that my mercury or the medium, the liquid that I had expands linearly, so I'm just going to divide the length of this thermometer from 0 to 100, the marks that I had made already, into 100 divisions, and it's going to give us a good scale of temperature. The thermometer now has a linear scale. In other words, we can also say that the thermometer has been graduated or it is calibrated now. So after this, between 100, 0 and 100, we divide them into 100 divisions or major 10 divisions. And then, this is going to be 10, 20, 30, 40, 50, 60, and so on till 100 like that. Okay, we've talked about liquid and glass thermometers and how scales of thermometers are made. Now, another really important type of thermometer is clinical thermometer. It's basically a liquid and glass thermometer, but with like a special property that is called a constriction. A clinical thermometer is a special type of mercury and glass thermometer, and it is used by doctors and nurses. The reason why it's a separate kind of thermometer is because it has a constriction after the bulb. Its scale usually extends over very few degrees on either side of the normal body temperature, so it has a really small range. Now, it's really important to first understand what these terminologies are. What does range mean? What does upper fixed point, lower fixed point mean? What does sensitivity mean? So a range is basically the difference between the highest value and the lowest value that, let's just say, if this is a thermometer, then thermometer, and okay, that's not the best thermometer. Okay, I wait. Okay, if this is the first marking on the thermometer and this is the last marking on the thermometer, so if we basically take a difference of them, it will give us the what do you call it, the range of the thermometer. So what this is saying is that in clinical thermometers, because they are to be used by doctors and nurses in hospitals, these thermometers don't really have a large range. They don't have a large range because those um, the temperatures that are to be considered are body temperatures, and they are over a really small range. They don't want to measure what's going to happen at 200 degrees or 300 degrees. So it's a really small range around the normal body temperatures. So because of the very narrow capillary means that it is the width of the capillary or is really really small. So that basically means uh, that that if there's an increase of only 1 degrees Celsius, the expansion or the increase in length of the mercury level is going to be notable. It's going to be more noticed than how it was in general liquid and glass thermometers. Because narrower tube you have, more change in length or easier visibility or more sensitive, basically it would be. This is called sensitivity. If something is able to measure or detect the change in a really small amount, then we say that it is sensitive. So because it has a very narrow tube, clinical thermometers are really sensitive. They also have this constriction just beyond the bulb, like right after the bulb, where the thermometer is placed under the tongue, the mercury expands, forcing its way past the constriction. So that basically constriction just makes a way out to the narrow capillary tube and causes the mercury to expand linearly. Okay. Thermocouple, and also that when since the reason why we have a constriction is because since the temperatures that we are measuring are in very small range, and let's just say a doctor has taken the temperature of a patient and then he's just reading it, it's really easy to just imagine that temperature is dropping right after that because the temperature of the environment is going to be different. And since the thermometer that we're using is really sensitive, so that thermometer might just change its reading right after the doctor took it out of the thermometer, sorry, patient's tongue or armpit, wherever he was measuring it from. So the constriction basically, makes that process of uh, contracting back or getting to a stable temperature a little delayed because the when the mercury level comes back to the bulb, so it has to go through that constriction, which makes it like a longer um, delayed process. So thermocouple thermometers are really important thermometers too. A thermocouple thermometer consists of a wire of two different materials such as copper and iron, and they're joined together. Since we have two different materials of wires, they have different resistivities, they have different resistance that they are to offer. So even if they are of the same length, they are going to offer different resistance. So when uh, one junction is at higher temperature than the other, an electric current flows, and the electric current flows because of difference in potential difference, and it produces a reading on the sensitive meter, which is then dependent on the temperature difference. So the temperature difference basically causes the electric current to flow, which is due to the potential difference that is between the two junctions, the cold junction or the hot junctions of the different wires. And the potential difference is then measured through a digital sensitive voltmeter that is shown right over here. And in this case, thermocouple thermometers are thermometers in which we don't get reading. We don't get the reading in really temperature terms. We get it um, in terms of voltmeter, sorry, in terms of voltage or potential difference, and then we calibrate that voltage in terms of thermometer. Let's just say if I know that I had this one cold junction, let's just say cold junction is at a fixed point, which is zero, melting melting ice. It's just at melting ice. We're not changing this. This is just a constant. However, at hot junction, I first of all I placed my a beaker full of steaming boiling water. So now I know that steaming water is again at 100 degrees, but what I need to see is that what reading is this voltmeter gonna give. Let's just say it's giving this minus 19.99. So I'm basically going to then calibrate it and use another known source to see what the voltmeter gives the reading, and then tweak it up to calibrate it into a temperature scale. Other thermometers, there are different types of thermometers. One type of thermometer is a resistance thermometer, which uses the fact that electric resistance of a platinum wire increases with temperature, and and a resistance thermometer can measure temperatures accurately in the range of minus 200 to 1200, but it is bulky and best used for steady temperatures. A thermistor, it can also be used, but it is over a small range. A constant volume gas thermometer uses a change in pressure of a gas to measure temperatures over a wide range. And again, it is very accurate, but it is a bulky and a very, you know, very and it does include a lot of instrument and a network of instrument in it. Um, and then we have thermochromic liquids, which change liquid when temperatures have a limited range around room temperature. So we're going to now see the pictures of these basically. I didn't really mention this, but this is industrial type bimetallic thermometer, which again uses the contraction or expansion of bimetallic strip in order to measure the temperature or to calibrate it. This is thermistor, it changes its resistance with change in temperature. This is a thermochromic temperature thermometer, which changes its color or shows us different color when it is put on that surface. And this is a constant volume gas thermometer. So all of these are very accurate and they have their own applications in their own terms. This is about it with the thermometers chapter.